ask questions before the time. But when you ask a question, if you can tell us your name and what team you're from. So, it is my pleasure to introduce Sarah Masara from the University of Florida.
Hi, my name is Dana Macero. I'm from the University of Florida ASME student section, and I'm also the captain of our human-powered submarine team. And my presentation today is about our submarine, Small Thing 3. What is human-powered submarine? Human-powered submarine is a biennial collegiate competition. We have a competition every 2 years. We have about 25 to 30 people competing. The goal is to design and construct a single wet-person submarine whose propulsion is directly coupled to a human. So what that means is there is one person that goes in the submarine, and who's the pilot. It's wet, which means the hull is filled with water. So the pilot has to breathe off of scuba equipment. And propulsion directly coupled to a human, that means that we have like a bicycle drivetrain, and when the pilot pedals, it spins the propeller, which moves the sub through the water. At the last competition in 2009, U.S. placed second in innovation and fifth overall in the race. Here are some of the things I'm going to be talking about our sub today. Hull, nose cone, electrical control system, although since this is a mechanical conference, I'm just going to go over how the electrical system affects the mechanical components. Drivetrain, propulsion, control systems, and safety systems. The hull. The hull was designed and co-engineered to have the smallest cross-section in order to reduce drag. So what we did was we used this mold that we made and co-engineered, and we had it manufactured on a 5-axis CNC mill. So we took this half mold, and we used fiberglass to lay up 2 parts. We took these 2 parts and put them together to make the hull. And here you can see the mold and the fabricating. The hull has 2 hatches, a main hatch in the front, and this is where the pilot gets in and out of the submarine. And we also have another hatch in the back where the emergency buoy pops up. We also have aluminum plates, which are fiberglass into the inside of the sub, as you can see here. And we use that to mount the drivetrain and the harness to the inside of the sub. The sub is also lined with foam in order to maintain neutral buoyancy throughout the race. And our sub actually has an exhaust valve. Now, why would a human-powered submarine need an exhaust valve? Well, remember, this is a wet submarine. It's filled with water, and the pilot is breathing off of scuba equipment. So every time the pilot exhales, that air goes to the inside of the hull, and it collects at the top of the submarine. Over time, this can affect buoyancy. So what other schools do to solve this problem is they drill holes in the top of their sub, so the air can escape through the holes. But at UF, we wanted a more elegant solution. So what we did was we created a fitting for the scuba regulator, which for you non-scuba divers, that's the part that you breathe out of. We created a fitting with a hose attachment that goes directly to the hull, so that when the pilot breathes out, the air goes directly to the outside of the hull. And there's actually a picture of that. Nose cone. So here you can see the exhaust system. So the nose cone is made out of a clear plastic so that the pilot can see the race course. And our nose cone is mounted with cotter pins. Previous years they've used bolts, but there's about 12 bolts, and it took a long time. It was a pain to in each bolt, and the cotter pins will make assembly much faster. Electrical control system. Before you can understand the electrical control systems of a human-powered submarine, you must first understand how the sub can rotate about itself. So I brought our torpedo. This is not actually part of the sub, but when we go on scuba dives together, we use it to play catch underwater. So there's 3 ways the sub can move: roll, pitch, and yaw. Roll is when the sub rolls like this. Pitch is when the front of the sub moves up and down relative to the back of the sub, like this. And yaw is where the front of the sub moves left and right relative to the back of the sub, like this. Does that make sense? So we have automatic pitch control. So since this is a speed race and it's just a straightaway, straight track, you want to maintain zero pitch through the whole race. So how we do that is we have two pressure sensors, one in the front of the sub and one in the back of the sub. And these pressure sensors are used to calculate depth. The depth in the front of the sub is significantly different from the depth in the back of the sub. It triggers our elevators to move until we have zero pitch. We also want to have automatic yaw control this year. So on the race course, in the competition, there's a line of rope lights on the bottom so that the pilot can see where he's going. It's really dark and murky in the competition. It's an indoor swimming place, pool, military facility. So you're going to have a red cam that's going to keep track of these rope lights. And if you set the gear off path, you're going to have the rudder move until we're going along the path again. We also have variable pitch propeller. Now this isn't pitch as in roll pitch yaw, but pitch as in the angle of attack of the propeller blade. For every speed that the sub is traveling, there is an optimum angle of attack of the pitch of the blade, which will give the maximum thrust of the sub. We want to go the fastest so we can win the race. So in order to do that, we have this variable pitch system that will make sure that we're always operating at optimum thrust. So we have a velocity sensor on board the submarine and a microprocessor which calculates the optimum angle of attack. And we have a linear actuator, and the shaft in the linear actuator moves in and out, and that's coupled to a bunch of mechanical linkages which adjust the pitch of the propeller. Drivetrain. The drivetrain was modeled off of a single-speed bicycle chain and sprocket system. We also have a double gear. You can't really see it because it's in a housing, so it just looks like a roller box. But it's there, so that you can transfer the power of the pilot pedaling to spin the propeller. And this one doesn't have it, but we're going to have a free-floating chain tensioner. One of the biggest problems in competition is the chain slipping off of the sprocket. So in order to solve that problem, we have a chain tensioner. It's like two clips. They go on the top and the bottom of the chain and tighten together so that there's more, the chain is interacting with more teeth on the gear. And that's the tensioner. Propulsion. Our propeller blade was modeled off of a Clark airfoil. We have a three-base propeller which was designed in SolidWorks. So we took that SolidWorks model, we rapid prototyped it. And then we took the rapid prototype, you can see the rapid prototype now, and we put carbon fiber over it to make our blade. Now, in case you've never come across rapid prototype, it's just a type of 3D printer. So you take your spool of material, which is ABS plastic, and there's also support material, and put it in the machine. You take your SolidWorks or Pro E or whatever CAD model, you put it into the machine, hit the button, and it alternates between layers of the ABS plastic material and the support material. It goes layer by layer until it's done, and then your part pops out in a tray. And as you can see on the top part, the brown support material is stuck to your part when it's done. So you either have to chisel it off with a screwdriver or a knife, or you can put it in an acid bath and it will dissolve the material. Sinking system. Since this is an inherently dangerous activity, Swamp Street has lots of safety systems. First, we have a harness right here to secure the pilot inside of the sub. Now, when you're riding a bicycle, you don't really need help staying inside on the bike because gravity kind of does that for you. But when you're in a submarine underwater wearing a wetsuit, it's easy to float around inside the sub, which makes it hard to transfer all of your power to pedaling. Underneath the harness is our the pilot's air supply. This is your tummy tank, and at the top you can see the regulator, which is the part that the pilot prefers not to breathe, and also a pressure gauge, which tells the pilot how much air is left in his tank. We also have a spare air and latches on the hatch, which are accessible from the inside and the outside of the submarine. So the pilot can be inside the sub and be like, okay, I'm ready to get out now. Pull the latch and get out. Or in case of an emergency, the Navy divers can swim down, pull open the latch, get the driver out, and bring him up to safety. Now this buoy system. So there's a dead man switch, and when the dead man switch is activated, we have a buoy that pops up from the back hatch, and the Navy divers swim to the rope. So there's a rope connected to the buoy, and the Navy divers follow the rope to the sub, and follow it to the pilot, and then get the pilot out and bring him up to safety. We also have a beacon, which is pretty much just like a blinking flashlight on the top of the sub. It's a competition requirement, but it makes it so that you can see the sub from the distance underwater, because it's really dark at the competition. In case some of you are not scuba divers, I didn't know where the spare air was until I started scuba diving. It's an emergency backup tank, and in case something happens to your primary air supply, this emergency backup tank has about 20 breaths of air, just enough to get you from wherever you are to the surface safely. Control surfaces. Swamp Ring 3 has 4 elevators and 2 rudders. Elevators are the fins that adjust depth and pitch, and rudders are the fins that adjust yaw.